Hey, I thought today I'd work on another integral from the UNSW Integration Bee. This is from 2019, problem 28. We have the integral from 0 to pi sine 2019 over 2x over sine x over 2 dx. Okay, I thought this was really interesting because there is a formula for this that makes it very simple and very quick. So we actually could do this with the formula and do it in like 10 seconds and be done with it. But what I want to do is derive that formula and kind of go over it a little more. So the first thing I want to do is I'm just going to focus on this input to the sine function here. Let's just notice that we can rewrite that 2019 over 2. We could separate that out as 28 over 2 plus 1/2 x. And then this here, 2018 over 2 is just 1009. So we could write this as 1009x plus x over 2. So the nice thing about writing our numerator this way is now we can use the angle sum formula to break this thing up. And you notice because we have x over 2, we're going to have like some cancellation because we already have sine x over 2 in the denominator here. Splitting it up this way is actually going to be pretty nice. But the way I'm going to do this, I'm not going to worry too much about this 1009 because it turns out these problems are really similar with almost anything you put here. I think any integer, so like what I'm going to deal with is we're going to look at this as sine nx, where n is going to be like any positive integer. So we'll have nx plus x2. What I'll do is work on this general case, knowing that our n value is going to be 1009, and that it doesn't matter a whole lot what we choose for n. Okay, so we're just going to go ahead and look for an identity to simplify this, which is the same thing as our integral in this generic form, where we just have n on the x, where n is 1009. And like I said, we can use the angle sum formula up here on the numerator. Okay, so we're going to just apply this angle sum formula to rewrite this. So we're going to have sine, so this is going to be our a and this is going to be our b here. So we're going to have sine nx cosine x over 2 plus, then we just swap them. So we're going to have sine x over 2 cosine nx. But then we can just split this into two fractions. Okay, so we'll rewrite this again. But then here on the right, these sine x over 2's are going to cancel, so we just have cosine nx over here. That's very nice. Next, what I want to do is just focus on this numerator right here and see if we can simplify that a little bit. What I'm going to do is use this different angle formula that we have here, where for, in this case, our a is going to be nx and our b is going to be x over 2. So using this, we're going to have half sine nx minus x over 2. And then we're going to have plus half sine nx plus x over 2. And this is all going to be over our sine x over 2. Now what I can do with the angle on this one is, instead of writing it as subtracting a half, I can take the n down 1 and add a half. So I can write this here as, we can write this as n minus 1 x plus x over 2. What I've done here is gotten it more into the form of this original thing. And let's just, while we're at it, let's call this y sub n, okay, where n is our input here. And then we can put these things into this, because these look so similar, we can use this terminology. So what do we have? So for y sub n, here we have 1/2. Now this thing here is actually almost the same exact thing, but we just have n minus 1 as an input. So this here is y n minus 1, y sub n minus 1. This here is exactly a half times this, so this here is going to be actually half y sub n, and then we're just going to bring over our cosine nx. Okay, now this is some good progress, but what I want to do now is, because we have a y sub n term on both sides, let's actually just subtract a half y sub n on both sides. Okay, so then what we're going to have here is, on the left side, we're going to have half y sub n equals half y n minus 1. But then just one more thing I'm going to do is I'm just going to multiply both sides by a 2 just to clean it up a little bit. Then we have our expression for y sub n, and it's going to be, this is going to cancel here and here, so we're going to have just y n minus 1 plus 2 cosine nx. But now the beauty of this, we have this very neat definition for our y sub n. Okay, y sub n just being this thing, keep that in mind. So we have this kind of very nice definition that's just going to kind of reduce the angle on sine, and that's what we like. So we can just repeat this. So again, like if we want the expression, what is y n minus 1? Well, that's just going to be y n minus 2 plus 2 cosine n minus 1 of x. And of course, what we can do is we could just repeat this over and over and over again. In this case, 1009 times, but it doesn't really matter how many times. and we can get some kind of expression for this. So what we can do is put all this together and get ourselves a nicer expression for y sub n. So all these y terms are actually going to reduce all the way down to y sub 0. So I'll write that. But then here, we're going to actually have to sum all of these up. So I can factor a 2 out. So we'll have this summation of all these cosine terms. I can create another variable. We want to use something other than n. We're going to sum up to n, but we'll start at k equals 1, like this. So we have a sum of all these cosine terms. And this is not quite our formula for y sub m, is what we can do is something with y sub 0. We can just notice if we plug in a 0 in here, well, 0x is just 0. And we end up with, this is actually just sine x over 2, because this is nothing. So we have sine x over 2, sine x over 2, and this whole thing is actually 1. So what I can do in my formula is just replace that, and this is just going to be a 1 here. And what we've done is created a really nice formula that now, when we go and integrate this thing, it's going to be way easier. So if you want more information on this, you can Google Dirichlet kernel and you can find out some more. Okay, so finally, I think we're ready to integrate. So what we're going to do, noticing that this now, we have this expression for it, and we're just going to rewrite this. So we're integrating from 0 to pi. We'll plug this in, but instead of using the summation, I'm going to actually kind of write this out. So what this is, so for this sum, we're going to have cosine x plus cosine 2x plus cosine 3x all the way to cosine of n, but our n is 1009, so it's going to be all the way to 1009x dx. Now when we integrate this, we'll integrate 1, and we just have x. Then we'll have our 2 out front. Then integrating cosine is going to be sine x, and then we're going to have half sine 2x, a third sine 3x. Then finally, we're going to have 1 over 1009 sine 1009x, and this is all evaluated from 0 to pi. Okay, so plugging in pi, we're going to have pi in for x, we're just going to have a pi. Sine of 2 pi is 0, sine of 3 pi is 0. Sine of all this is going to be 0, so we're not worried about that. We plug a 0 in here, we get 0. And then again, we plug 0 in for all these sine terms. These are all 0 again. So again, what I mentioned in the beginning is it really simplifies very quick because like everything's 0. So all we have left is just this pi here. So our final solution is just pi. So that's it. Thought it was a great problem today. Thanks everyone for watching. Please like and subscribe. Have a good day.